Okay, so let's look at sort of the second half. Let me pull up my Word document. So we did this one. Now let's look at this over here. So the first part here, we're just going to kind of discuss this. We want to determine if the following are going to be exo or endothermic, sorry. Exothermic meaning it releases heat. Endothermic means it needs heat for that action to occur. Okay? So the first one is natural gas burning on a stove. Okay, so we're looking at the natural gas burning. Okay, that is going to be exothermic because anytime something's burning, you're releasing heat. Okay, think about a fire. Okay, so that'd be exothermic. Isopropyl alcohol evaporates from skin. Okay, so we have to think of evaporating. Evaporating is going from a liquid to a gas. Anytime you become more gas-like, that's going to take energy to do that because you need to basically be kind of heated up a bit. So that's going to be endothermic because you need heat to evaporate. Water, okay, let's look at the next one. Water condensing from steam. Condensing is actually the exact opposite of evaporation. Okay, so this goes from a gas to a liquid. You know, you've seen the condensation on your cup, and basically, it's usually, you know, you have like a cold cup, an ice cup of water. Well, you have your water vapor that's in the air, and basically when it hits your cup, since your cup is so cold, it cools it down and allows for that water vapor to condense onto your cup. Okay, so it needs to release heat to be able to do this. Basically, it needs to cool, which means the release of heat. Okay, so anytime you say something's cooling, again, you're trying to get rid of heat. Okay, so that's exothermic. So anytime you're becoming more solid-like, you're going to be exothermic. Anytime you're becoming more gas-like, you're going to be endothermic. Let's look at number 2. Consider the following equation for the combustion of acetone. Okay, so here's acetone, and a combustion reaction is when you react it with oxygen. Okay, and you're always going to release carbon dioxide and water. Okay, whenever you have this reaction, it releases negative 1,790 kilojoules of energy. Okay, so if you have a bottle of nail polish, which contains 177 milliliters of acetone, how much heat would be released by its complete combustion? The density of acetone is 0.788 grams per milliliter. Okay, so the density is important. So what we're looking at here is if we have basically 1 mole of acetone, this is how much energy is going to be released. But we don't want to just look at 1 mole, we want to look at 177 milliliters. Okay, so how much energy will be released from here? Okay, so let's look. We have 177 milliliters of our acetone. Okay, and let's see, numbers that we need. The density of acetone is 0.788 grams per milliliter. And then let me also give you the molecular weight of acetone. And this is going to be 58.08 grams per mole. And then remember, the delta H of the 1 mole of that is 1,790 kilojoules per 1 mole of acetone. Okay, so let's look here. We always start, this is how I know, okay, I have all these numbers. Where in the world do I start? And for me, I always start with the most simple units. You see, this is a gram per milliliter, this is a gram per mole, this is a kilojoule per mole. This one's just a milliliter. It's not a combination of units. So let's start there. 177 milliliters. And we're trying to get energy. Energy is always going to be in joules. Okay, so well, in this case, it will be kilojoules just because that's what that unit is. So we're trying to get this as our final unit. So we're going to use all of these numbers to cancel out. So if we start here, the first thing we need to cancel out is milliliters. Okay? Now we want to go, so we have a milliliter. So what unit in here has a milliliter? This one, right? So we're going to use that one first. We have 1 milliliter is 0.788 grams. Okay, that's how we cancel out milliliters. But we don't want grams, we want kilojoules. Okay, so we need to cancel out grams. Okay, so we've used this one, we've used that one, we've used this one. Okay, now which unit that's left has a gram in it? This one, right, has a gram. So it says here we have 58.08 grams per 1 mole. Okay, so we use that. Okay, we don't want moles again, we want kilojoules. And let me also say, I have that this is kilojoules per mole. Let me go back here to clarify this. It's 1 mole because there's only 1 acetone. If we were looking at oxygen, that would be 4 moles. So I would have written here, let me come back. I would have written, if it was oxygen example, it would have been 1,790 kilojoules per 4 moles of oxygen, okay? Or if I was looking at water, it would have been per 3 moles, okay? So that's how I know how many moles, because I'm looking at it in the equation there, okay? So that could be a problem that comes up in your homework, and if you miss it, that might be why, because it's not always per 1 mole, it just depends on the reaction. So when you come across a problem like this, just keep that in mind. Okay, but this one is per 1 mole, so we have 1 mole, and that is negative 1,790 kilojoules. So moles cancels, grams cancels, leaving us with kilojoules. So if we multiply and divide this all out, you should get negative 4.3 times 10 to the third kilojoules. Okay, so this tells us, this says, in the original equation, if I have 1 mole of acetone, I will get this much energy from combusting it. Think about like gasoline. You know, gasoline makes our car go, and it does that by combustion. So the car combusts the gasoline and allows it to go. Well, instead of using gasoline, it says, well, let's combust nail polish remover or acetone. Okay, so when you do that, if you have 1 mole of that, you get this much energy. Okay, but we don't have 1 mole of it, we have 177 milliliters. So how much energy do we get from that? We get negative 4.3 times 10 to the third. Okay? Let's look at another problem. This is a bomb calorimeter problem. Okay, it says when 0.514 grams of C12H10 undergo combustion in a bomb calorimeter, the temperature rises from 28.4 to 29.4 degrees Celsius. So let me go ahead and start writing some of this down. Okay, we have a bomb calorimeter. Bomb calorimeter. So there's things that we need to know. Bomb calorimeter is at constant volume. And so in this, we know that delta U equals to Q of the reaction, we should say. Okay, and that's any time with a bomb calorimeter. Now remember, if we have a coffee cup calorimeter, Q equals delta H. So there's a difference there. And we should also say that Q of the reaction is negative Q of the calorimeter. So initially when you do this problem, you're going to find Q of the calorimeter, the energy released from the calorimeter, and you need to change the sign to get the Q of the reaction. This is always, so anytime you do a bomb calorimeter problem, you need to do this. You have to remember this. Okay? And also remember that in a bomb calorimeter, you have actually Q is C delta T instead of M C delta T. So let's look at our delta T first. We have our temperature initial, or we'll do temperature final minus temperature initial. So our final temperature from the problem, so I already have it written down, was 29.4, and our initial temperature was 25.8. Okay, so if we, and this is in degrees Celsius, if we subtract that out, we should get 3.6 degrees Celsius. That is our change in temperature. Our C let's look at the problem here. Find the internal energy of 0.154 grams of that in kilojoules per mole. So we want kilojoules per mole. The heat capacity, which is C, of the calorimeter is 5.86 kilojoules degrees Celsius. So C is 5.86 kilojoules per degree Celsius. Okay, there is a mass in there. Let me write it down over here. Mass is, what was it, 0.514. So remember, when you have a bomb calorimeter problem, the Q becomes C delta T. It's not MC delta T. They're pretty much always going to give you a mass, though, which is going to throw you off. You're going to be tempted to put it in here, but don't, okay? The reason the mass is in there because our final unit, what we're trying to find, is delta U in kilojoules per mole, okay? And we're going to use this grams to find the mole part. Because if we look here, let's plug everything in. We have Q equals to C, which is 5.86 kilojoules degrees Celsius. Okay? And over here, delta T is 3.6 degrees Celsius. So our delta C, or our C, sorry, cancels out, and leaving us with what number, or what unit? Kilojoules, right? So if we multiply this, we get Q is, let me see, 21.1 kilojoules. Okay, so we're going to have kilojoules because that's left over. Now here, do you see, it wants our unit in kilojoules per mole, but we only have kilojoules, so we have to divide it by moles, and that's where our mass comes in. Okay, but first, when we calculated all this, this was all from the calorimeter. Calorimeter. So the first Q you always find is of the calorimeter. So if Q, the calorimeter, is 21.1, let's look what we wrote down here. To get Q, the reaction, we have to change the sign. So it's always the opposite sign. So it's the same magnitude, so the same number, but opposite sign. So if this was a positive sign, but let's say it's a negative, then this would have been positive. Okay? So we know Q, the reaction, is negative 21.1 kilojoules. Now we want delta U in kilojoules per mole. So let me, here we go. Now we need to get moles here. We have the kilojoules, so we need to divide by moles to get the correct answer. We have 0.514 grams, and anytime I go from a grams to a mole, remember I'm going to use molecular weight, always. Okay, and we need the molecular weight of the substance. It was C12, let me see what it was, C12H10. So if you did that, if you have, carbon weighs 12 on the periodic table, and we have 12 of those, plus 10 hydrogens, and those weigh 1 gram per mole. If you add those together, get to the molecular weight, you should get about 154.2 gram per mole. Okay, so if I put this in, I have 154.2 grams per 1 mole. I multiply this out. How many moles will I get? Let's see, I get 0.003 moles. Okay, so I have my kilojoules right here. I have my moles right here calculated. So now I need to divide them. You see, because I want it in kilojoules per mole to get the final answer. So delta U will be negative 21.1 kilojoules per 0.003 moles. Okay, so when you divide that, you should get negative 6.3 times 10 to the third kilojoules per mole. And I would say 99% of the time you're going to have to go through this whole thing. You're going to have to, realize your first Q is Q the calorimeter, so you need to change your sign. And then your final units need to be in kilojoules per mole, so you'll get kilojoules, and then you need to calculate moles and divide it. Okay, so just remember to do that on your bomb calorimeter problems there. Okay, let's do a Hess's law. Now I'm going to kind of do a shortcut here, and hopefully you follow what I'm doing. So let's just look at this here. Now what you're going to do, what we're manipulating is our delta H's, okay? This is what our answer is. We want to get this reaction, okay, using these. So this is what I do. I look at my product. What do I want my product to look like? I want iron in my product, and I want 2 irons. Okay, so let's look what I have here. Do you see down here, here are my 2 irons, okay, but I want it, this is a reactant, not a product, so I need to switch it. I need my iron to be over here. Anytime you switch a reaction, you have to change that sign. So our new delta H for that reaction, I'll call it delta H1, it was, let me see, I don't remember. It was negative 824.2. You see that negative right there? And anytime you flip it, because I need to have my iron over here, I'm going to change it. So now it's positive 824.2. So our first delta H is going to change to 824.2, and that's a positive kilojoules. Okay, now let's look at my other product. So now if I flip this over, it would have 2 iron in the product over here. But the other product I have is 3 CO2. Okay, do you see that CO2 is already in the product? Okay, so that's good. I don't have to flip anything over, but I do need to multiply it by 3 because I need a 3 there. So I have to multiply everything by 3, including the delta H. So my delta H2, I need to get this number and multiply it by 3. Okay, so my delta H2, I'm going to do 3 times negative 282.3. Okay, so basically, I'm trying to make this, like, you see the products I have here, I need those to look exactly, those products to be on the products over here exactly. So I already have 2. Now let's say I didn't have a 2 right here, it was just a regular iron with not a 2 in front of it. Well, I would still have to flip it over, and then I would have to also multiply everything by 2. So this would be a positive and then multiplied by 2. Okay, so you manipulate these here to get this, so the products look the same. Hopefully you could follow that. So now that I've manipulated the products, now I can add these together to get my delta H I'm trying to get. We'll say our delta H final, because I've manipulated it to do that. So if I do 824.2 plus 3 times negative 282.3, we will get negative 239 kilojoules approximately. Oops, I don't even know what that looks like. Kilojoules. Okay? And now let's look at one more. And this is a heat of formation. So we're looking at this reaction here. CO plus H2O yields to H2 plus CO2. And you would have to look up in a chart and you look at the heat of formation. These are in the back of the book. And if you did a problem on the exam, they'd have to give you these numbers. So the energy it takes to form CO is negative 110.5. And the energy it takes to form water is negative 24.18. Hydrogen is 0, and CO2 is negative 393.5. So these numbers would have to be given to you, or you'd have to look, in a chart, and you could just look up. If you don't have the book, you could look up online just heats of formation. Okay, so you would say heats of formation for carbon monoxide, heats of formation for water, heats of formation for hydrogen or carbon dioxide. Okay, and they would give you these numbers. Now what you do, it's products minus reactants. Okay, so what we do is we add up how much energy it takes to make these, okay, and how much energy it takes to make these, and we subtract them to get the total energy for the whole reaction. So to make my products, okay, it takes, here are my products over here, products, reactants. I have negative 110.5. Now, how many of those do I have? You say I just have one? Okay, so I just multiply that by 1. Now, let's say there, 1. If there's a 2 in front of there, then I have to multiply this by 2, because if we times 2, because this is the energy to take 1. Plus, I have 1 water, and it takes, multiply, 24.18 kilojoules of energy to make it, kilojoules per mole. Now, if I add this together, I will get, let's see, reactants. Oops, I put products. This is my reactant. I don't know what I'm doing. This is reactant. Sorry. Here are my products. Okay, so here are my reactants because they are reacting together to form the products. And my reactants get negative 352.3 kilojoules. Okay, so it takes to form CO plus H2O, to form one of each of those, it takes 352.3 kilojoules of energy. Now let's look at our actual products. Okay, 1 hydrogen molecule, but that takes 0 energy, plus there's 1 CO2, and that is negative 393.5 kilojoules of energy. So now let's add this together, and let's see, we get negative 393.5 kilojoules. Okay, so the energy it takes to form our products is negative 393.5. Okay, but now we want to look at the overall reaction. Okay, so the formula is, let me change the color. We take what we got for our products and we subtract that from what we got from the reactant to get delta H, we'll say overall or total. Okay, so our products, we get negative 393.5 kilojoules. Our reactants take, says products minus, and it takes negative 352.3 kilojoules. So we add, so negative 393 minus a minus 352.3, remember to put that negative, extra negative into your calculator, you will get 401.2 kilojoules of energy. So this reaction needs 41.2 kilojoules of energy to occur. Okay? So those are some good examples. Hopefully this helps you. I'll do chapter 7 soon.